Okay, today we're going to do sort of the second part of problem set 1, and then I'll send out a quiz later, right? Well, I guess I'll post it on Sakai, right? That's how we did it for you guys. Yeah, okay. It'll be doing like a week. And then we'll also get into this long chapter 2 on the sort of the general. We'll get into the general theory of transduction. Now, old business. I was having a little bit of trouble yesterday with this. The sign here is almost always not important, but if you really want to know it, what's stated in here is correct. I was bothered by something I shouldn't have been. So this is correct, this statement here. If you really want to know this sign, you just have to, you can look at either the x or the y. These are known, these are measured quantities here. Once you know phi, then you can get f. And in particular, you can resolve what this sign is if you want. It's no problem. But like I said, usually no one cares. Okay, so now we're going to do the textbook problems. The first, and I think the third one or whatever. Okay, so the first one has to do with this standard model of a damp-driven simple harmonic oscillator. Okay, here's a diagram of the system, and we're going to, this is kind of an interesting problem. We're going to find the input mechanical impedance. All right, so there's an external force here, F. Some external agent is exerting this oscillatory force, capital F. And that agent's going to feel an input impedance, which is defined to be the complex force divided by the complex velocity at this point, which is the same velocity as the mass, you'll notice here. Okay, so why are we going to do that? Well, an alternative way of, this is obviously an important quantity, right? We're going to be dealing throughout this course in input impedances, electrical and mechanical, because we're dealing with transduction, going both ways. So an alternative way of doing this is go to the equivalent circuit and find the equivalent electrical input impedance. And then you just make the impedance analogy correspondences, and we should get the same answer. So it's an exercise, but I think it's an interesting one. All right, so let's do and it's also interesting for another reason that I'll point out to you. So let's do the mechanical one here. If you look at this bar right here, this is of course a massless rigid bar, right? There can be no net force on it, because if there were, it would have infinite acceleration because it's massless. So the forces have to balance on here. Now there's two ways of doing this to proceed mathematically. You can set the sum of the forces. There's a force due to the external agent. This mass exerts a force here. This spring exerts a force, and the dash pot exerts a force. You can sum all those forces and set it equal to 0. Or you can deal with a balance. I prefer usually a balance. This will also come up when we deal with voltage in this course, and I'll remind you when we do. So I've done the balance approach here. This force has to be balanced by these forces. Now the meaning of these forces, when you do it the sum way, when you sum all the forces to 0, this would then be the force of the mass on this. When I do the balance here, it's going to be the force on the mass. The force of this rod on this mass is equal and opposite to the force of the mass on the rod by Newton's third law. So it's just, for me, it's a little cleaner. And now that I'm thinking about it, maybe I should switch back to the more pedestrian, sum of the forces equal to 0. The relationship between the forces here, the way I do it, with the balance of the forces, I'm looking at the force on this mass, which I know is the mass times the acceleration. If you do it the other way, where you sum the forces and set them equal to 0, then you have to put a minus sign here, because you're looking at the force of the mass on here. So that's why I like the balance method better. You can do it any way you want to. And incidentally, like I said, let me repeat, this idea of balancing will also come up in Kirchhoff. It also comes up in Kirchhoff's loop rule. So we'll see this again, but you can do it any way you want to. You just want to make sure you do it correctly. So here my F's are the forces on here, which are equal and opposite of the forces on the rod. So I know from Newton's second law that it's going to be this, and because everything is steady state here, the time derivative just brings down an I omega. The force on the spring here is, if I do a positive X, I compress the spring, I'm exerting a positive force, so it's just the displacement over the compliance, right? We're headed towards impedance, so I'm going to express this X as U divided by I omega, the time integral, the opposite of the derivative. Finally, the dash pot is just going to be the mechanical resistance times the velocity. That's the force that I'm exerting, that's being exerted on it. So I substitute these expressions into our force balance equation. I get this, and now I solve for the input impedance, which is the force divided by the velocity. These are all complex quantities, and I get this. And I can I can factor out an I, represent this as the resistive and you know, the reactive parts, and we get this. And you are well familiar with this from 3119. This got beaten into you in 3119, right? So we know that's the right answer. Now, here's the equivalent electrical circuit, and of course the impedance analogy. It's just a simple series circuit. What's the input impedance here? Well, it's the complex drive, which is the voltage, divided by the complex response, which is the current. And now everybody knows how to do this, right? We just sum because it's in series, we just sum the impedances. This is just electrical circuit analysis. So I know the impedance of the resistor is R, the impedance of the inductor is I omega L, impedance of this is 1 over I omega C, the capacitor, and I just immediately get the answer. Right? Now, to complete the problem, what we should do is we should do the correspondence. We should set the electrical resistance equal to the mechanical resistance. Replace L with M, and replace C with the mechanical compliance. And if you do that, you'll see that you get exactly that. All right? So this is an exercise. It's a good exercise, I think. And it points out something important that I promised you that we would do, and we'll do this several times. Which calculation would you rather do? Okay? You can see this is you have to think more. You're more likely to make a mistake. It's much easier. So this is one of the main reasons why transducer people use equivalent electrical circuits. Much easier. Okay, any questions about that one? Okay, the next one is the 1.3. And this deals with admittance. I don't think, we didn't talk about this last quarter, I don't think. Yeah, we haven't talked about it. This is the first time we're talking about it. It's simply defined to be the reciprocal of the impedance. That's all. So you might say, well, that's simple. Why does it have a name? Well, this can be, especially in transducers, it can be much more convenient dealing with admittance rather than impedance. And that may surprise you because it's just the reciprocal here. But remember, these are complex quantities. So they're in their complex plane behavior. The behavior of these in the complex plane is very different. And often this is very simple, and we can get useful information from it, and you'll see that in the laboratory in several experiments in this course. So it's so important that we not only have the name for this, we have the name for the real and imaginary parts. Remember, for impedance, we have the resistance and the reactance, right? You know that well. Here, the real part's called the mechanical. It's the conductance in general, whether it's electrical or mechanical. This is the conductance, and this is the susceptance. Okay, so the problem here, Brian refers to a figure, but it happens to be the same as what we just did, the standard simple harmonic oscillator. That's what we're going to deal with here in this problem that we just looked at. The impedance is just the mechanical, this is the input mechanical impedance, is the mechanical resistance plus I times the reactance, and you know this, and we just showed it, that the reactance is given by this expression. Okay, now we're going to deal with the admittance, which is the reciprocal, right? And now you can see it's very different because it's complex here. And maybe I should just get to the point here. The point is, one of the points here is that the admittance is 1 over the impedance. The conductance is not, in general, 1 over the resistance. You know, just because these quantities are reciprocal to each other, the real and imaginary parts aren't. And you can see that very easily right here. We're going to find the real and imaginary parts of the admittance here. Okay, so I've substituted the impedance. This is the reactance. This is the resistance, and this is the reactance. And now we're going to find the real and imaginary parts. And if you go through this, you can see that this is not simple. This is very standard in complex arithmetic. We clear out, we make the denominator real by multiplying by the complex conjugate of this, and we keep the value the same by multiplying by 1 here. So we carry this through, and then we can eventually identify the real part, called the conductance, and the imaginary part, which is the susceptance. And you can see here that G is not 1 over X, right? And B is not, G is not 1 over R, right? And B is not 1 over X. This is more complicated than that. And that actually turns out to be important because, as I said, things can actually be simpler in the admittance plane rather than the impedance plane. And we'll see this a number of times in this course. We'll see it first in this problem right here, in this particular problem. Now the next part is to look at what happens as we change frequency. In general, the real and imaginary parts are functions of frequency. Now the impedance here, you know, this is a constant. It's not a function of frequency. But in general, it can be. But this is clearly a function of the frequency. So what happens as we go from a 0 frequency to infinite frequency? Well, if you look at the values here, and I'll let you verify this. It's very simple. You know, as the frequency goes to 0, this goes to negative infinity. Right? This is constant. As the frequency goes to infinity, this goes to positive infinity. Anyway, you look at the behavior of the real and the imaginary parts of the admittance here, and you can see that at 0 frequency we get this, and I've evaluated an intermediate point here. This is the mechanical resonance. This is the resonance frequency where the reactance vanishes, right? That frequency is omega naught. There's the expression for it, standard expression. You get this, and you'll notice here that if you look at the values, we're returning to our initial value. So this actually makes a loop, and that's what's convenient about this. It makes a loop in the admittance plane. It doesn't make a loop. You can show that it doesn't make a loop in the impedance complex impedance plane, but it does make a loop here. And that can be useful, as you'll see in the laboratory, and as we'll discuss in the lectures later in this course. So it makes a loop. So here's the complex admittance plane, right? The real part and the imaginary part. We started at 0 frequency, we're at the origin, and at infinite frequency, we're at the origin. So we're going, as we increase frequency, we're going either clockwise or counterclockwise. The natural question is, which way? Is it clockwise or counterclockwise? And to get that, a simple thing to do is to look at instead of exactly 0 frequency, look at a small frequency. Mathematicians denote this sometimes by 0 with a plus sign up there. I don't know if you've ever seen that before. That means it's, you know, slightly, I've written it here. It means slightly greater than 0, okay, as opposed to 0 minus, which means slightly less. So if you go back, and I'll leave this for you to do. you go back and look at these expressions here and analyze. Just think, you don't have to write anything down. You just have to look at a small positive frequency. You'll see, and you can just do it right in your head. What you'll find here is that you have a small positive imaginary part. So that means we're going clockwise, like I've just shown here with the arrows. And you can also look at, you can look at when you approach, when you have a very large frequency, you can do a similar analysis and you'll find that you're down here, that the imaginary part is negative. Now, it turns out in this case that the loop is a circle. And Brian tends to treat all systems like you're going to get a circle. And it's not true, okay? We'll encounter this later in the course, but I just want to point it out to you now that you don't always get a circle. We're going to get a circle here due to the simplicity of this system. But in general, you get these loops, but they're not necessarily circles. Although sometimes they can look very close to circles, as you'll see. All right? But I just want to point that out because it's going to come up later in the course. So, in this case, how do we prove this is a circle? Well, the natural thing to do here is, we're in the complex plane. We look at, you can think of these complex numbers as vectors, right? They have a real part and an imaginary part. The natural thing to do is look at this vector or complex number, which I've called r here, little r. If we look at that, the modulus of that should be a constant. As we go through frequency from 0 to infinity, the modulus or amplitude, whatever you want to call it, should be a constant. So that's the approach we're going to take here. So we need to write down what r is. And these aren't vectors, but we can think of them as vectors. One nice thing about complex numbers is I write down this point here is the admittance here in the complex plane. It's a complex number. To get r here, all I have to do is take this y and subtract this complex number, which happens to be real here. Subtract this 1 over 2r. So r, this has to be equal to simply this value here minus this value. So I write that down, substitute the expressions for the real and imaginary parts of the admittance that we just calculated. Okay. Make sure we subtract off this. And then here's the real part of little r, here's the imaginary part. The square modulus is going to be the sum of the squares, of course, right? So here's the real part squared. Here's the imaginary part squared. And now we got some algebra to go through. It's not trivial, but it's very straightforward. And if you can find a simpler way, let me know. Or you just crank through this. And eventually you get that it is indeed a constant. This, the value of this is independent of frequency. So that tells us that it's going to be a circle. And furthermore, the circle has radius 1 over 2 times the resistance. Now, I think I made a note in here I hope I did. Yeah, so way back here, just for convenience, these are mechanical. We're talking about a mechanical system here. These R's is the mechanical resistance. I've dropped the M subscript just for, there's no way I was going to write that for all this, right? It's crazy. I'm not going to carry M subscripts along here. So this is the mechanical resistance. And now you can, we'll talk about this later in the course, now you can see why this can be useful. Experimentally, if, you often want to know that all the parameters, in particular this mechanical resistance here. So if you've got this actual transducer, you can plot the admittance, and then we have electrical boxes here, equipment here that will plot admittance And you plot this, and you just take 1/2 the, measure the diameter and take 1/2 that. Well, you take the diameter. From the diameter, you can get the mechanical resistance. So that's one of the uses. That's why this is important here. You can determine that parameter for an actual transducer. Okay, are there, I think that's it. So I'm going to edit, the solutions need to be some editing, so I'll edit those just like the last quarter, right? Well, except last quarter I would edit it before we actually did the, these are in a pretty good state, these typed solutions. They weren't typed last, right? So usually it'll be after the class, I think, so I'll post them. And there will be occasional editing of the actual problem assignment document, the problem set. I see that I have, but I'll put this stuff on Sakai, and I'll send out a message to tell you, and probably attach the document in the message too. Okay, so any questions? All right. That took a while to open up. This is a long chapter. Okay, so now, as I mentioned to you earlier, we're going to do this. There's actually a, oh, I hate it when it does this. I don't know, I have to go back. God. I don't know why it does that. Okay, I do this. And I do that. Okay, so roughly 5 years ago when I was preparing for this stuff, for the first time teaching this, I was amazed to find this general theory. It's actually very interesting, and it caused me all kinds of conceptual problems. I struggled with this for weeks, okay? And one of the reasons is transducer people, tend to be highly hands-on, experimental people, building things. They're usually not the greatest authors. They're usually not, and to be fair, transducers are complicated. So you're just not going to find a transducer textbook that is very friendly and nicely explains everything to you. Okay, I shouldn't say that because transducer people they're more physical than verbal. There's some truth to that, but another problem is there aren't that many courses in transduction at universities. Most people pick it up, most graduate students pick it up in the lab. That's how they learn it. So, so I had a lot of trouble understanding what Brian was saying, but I just kept struggling with it, and finally it started to make sense, okay? He doesn't say everything that needs to be said, but you never can, of course. So what we're going to deal with here, oh, and we're going to find that equivalent circuits play a fundamental role, a very important role here. That's why that's in the title. We're going to consider the standard case of where we have what's called a 2-port or 4-terminal transducer. And this is almost always what we'll be dealing with in this course. There's an electrical side. You have one electrical input, basically, and one mechanical output, or it goes the other way. Right? You can have a mechanical input and two, and then mechanical input, and then an electrical output. We will encounter some cases where there's multiple of these, but it's unusual, but it can happen. But this is the overwhelming standard case. And now, so how do you do a general theory on this? Right? It would seem to be impossible. It seems like, oh, you're going to have to take you can't do a general theory. You're going to have to take a specific transducer and analyze it. Well, it's not true, okay? And so that's what we're going to go through here now. So the first thing you do, and you can get surprisingly, a lot of mileage out of this, is we're going to assume we have a linear transducer. What we mean by that is that at a given frequency, everything's going to be, in general, a function of frequency here. All these parameters, right? The parameters of our transducer are, in general, going to depend upon frequency. So at a frequency, if you, the best way to say it is, all of these variables here, and here they are, V is the voltage across, F is the drive on the radiating surface, I is the current across the electrical input, and U is the velocity of the radiating surface. These variables all have to be linearly related. All right? Now, we've discussed this before. The linearity is very important. It allows you to have a, often you want to find out, like for the surface wave height demonstration, you want to measure that surface wave height. So once you know the sense, if it's linear transduction, and it's flat, which it, independent frequency, which it is in that case, there's just one number you deal with. It's the sensitivity. There's so many millivolts per millimeter. So once you measure electrically with the probe there, once you measure the millivolts, you just take this sensitivity and you immediately find the millimeters. That's the goal of transduction, right? That's the basic goal. So it's extremely convenient to have a linear transducer, and most transducers have some regime. Almost all transducers have some regime over which they are linear. And commercial transducers, things that you buy, one of the reasons that they tend to be expensive for quality, measurement quality, accurate measurement quality transducers. One of the reasons they tend to be expensive is a lot of effort has gone into expand that linear regime. Okay? So, once we make that assumption, we can write these two expressions here. These are important. They're called the canonical equations of transduction for the two-port system. And you can see everything is, we've written down a general linear relationship for the voltage and the force as a function of the current and the velocity. And that threw me. Why do we choose, I would think that we would choose voltage and force to be the independent variables, not current and velocity, right? These are like response variables. I think we should choose the drive variables as the, well, okay. So a few days went by and then I finally figured it out. And they don't tell you, Brian, and not just Brian. I got these other books too, I told you, right? No, but they don't tell you. Here's what's happening. We want to deal with impedances. They're very convenient. So we can choose as the independent variables to be any two variables we want. It's just convenient to choose the current and the velocity, because then you see these coefficients here. These are parameters that characterize our transducer. They're going to be impedances. See this right here? This quantity right here, you can see it's like a voltage divided by a current. That's impedance. And similarly for the mechanical impedance. Now these quantities right here, these are called the, so we have these impedances here, the electrical impedance, the mechanical impedance. You see, if you don't worry about this Zm is just the force divided by the velocity. The coupling terms here, this is the whole point of transduction. You can see that mechanical motion gives a voltage. That's transduction. So this TEM here, you want to read it going from right to left. This is the transduction coefficient going from mechanical to electrical. This one over here is going from electrical to mechanical. And in general, these are different. But there is a strong connection between them, and it's called reciprocity, and we'll start talking about that next week. We'll talk about that next week. Okay. Oh, another thing. You'll notice there are capital letters and lowercase letters. This is very important. This can be a notational nightmare, transduction, okay? The capital letters refer to an electrical quantity. The lowercase letters refer to a mechanical. See this M here? There's going to be a capital M. It's coming up, right? So, and you'll notice here, this is, I didn't notice this until last night. I never thought about this before. Why did they choose electrical to be capital and mechanical to be small? You know, they could have done either, right? They could have chosen this to be a lowercase and this to be an uppercase. Well, you're going to see the answer. And it's natural. It's when dealing with a transducer, it's much easier to deal electrically with it than mechanically. If I want to probe my transducer and quantify it, it's much easier to do electrical measurements than mechanical measurements. So we will see this again and again in the laboratory. So I think that's my theory of why they've capitalized that. But it could have been just happenstance. I don't know. But you need to keep this in mind, okay? So here's a diagram that represents the transduction. In our minds, we separate. We talk about a mechanical side and an electrical side. In almost all transducers, they're just intertwined. They're just one, and they're all together. Okay, but this is a sort of an abstraction that allows us to think about it. Now, there's another diagram that Brian has. I've never liked this diagram. Here's a kind of a little more elaborate or more specific diagram. And I don't think it's that great of a diagram, but it does give us it does tell us one thing. What it conveys here is that, let's say you're driving this you have a source. I'm sorry, let's say you have a receiver. So there's some acoustic wave coming in here, and you're going to convert it. You have a microphone, you're going to convert it to an electrical signal. You can see here that if this transduction coefficient vanishes, what this is conveying is that you're not going to pick up anything here if this is 0. Similarly, if this is like a loudspeaker or something generating sound, if you're driving here and this is 0, you're not going to get anything there. But anyway, I wouldn't pay too much attention to this. And we'll talk about this later. Maybe this is why Brian put this in there, so he could put loads on here. I don't know. Okay. Now we need to get a physical feel for these equations. There's a lot in these equations, and here's how we do it. Remember, impedance always has the general form: drive divided by response, right? So we're going to go through and come up with, from that canonical equations, we can come up with expressions for, or the meanings, the physical meanings of these impedances here. Okay? Now, even though these are impedances too, but they're called transduction coefficients. And I didn't, this is kind of embarrassing, I didn't realize this until last night when I was looking this stuff over. They are actually transfer impedances, right? The engineers use this word transfer impedance. Remember, I introduced this to you last quarter to understand reciprocity. The transfer impedance is symmetric if you flip source and receiver, okay? So I need to, I'm going to edit this in here, that we can I think I wrote, did I write this in here? Oh, I'm not, hold on. Make sure, I gotta make sure I got this, yes. Okay, so let me explain, okay? Let me explain. Here's the physical meaning of the electrical impedance, this ZE here. You'll see that when we have no mechanical motion, the interpretation of this ZE is just the input electrical impedance. It's the electrical impedance when you have no mechanical motion in that special case. This is so important in transduction that we have one word that we associate with this, so we don't have to say no mechanical motion. We use the word blocked. Blocked in transducer theory means that there's no mechanical motion, which mathematically means U is equal to 0. So we can write that the physical meaning of the electrical impedance here is the voltage divided by the current, the usual thing, under the condition of a blocked system, U equals 0. That's the meaning of the electrical impedance. And the mechanical impedance, very similar, right? You know, it's going to be symmetric here. The mechanical impedance is the force divided by the velocity, and that's for no current. And again, you can check this. You look at this equation. When we have no current, excuse me, when we have no current, then the meaning of this impedance here, it is the mechanical impedance, this pure mechanical impedance, the force divided by the velocity. So, when we have a name for this, for no current, it's called open circuit. When you open a circuit, you can't have any current. So that's the physical meaning of this, of the mechanical impedance. This quantity right here is the mechanical impedance, the force divided by the velocity, but only if you have an open circuit. Now, what about these transduction coefficients? Well, we can think of these, as I just told you, as transfer impedances, because this is an electrical, you know, this is a voltage, this is a drive, the electrical drive divided by the mechanical response. So you can actually think of that, and we should think of it that way. And it only took me, you know, like 6 years to realize that. So I'll write that in. And going the other way, right? And let's check this. Let's look at TEM. Let's look at the first expression here. How do I interpret this? Well, you can see that when there's no current, when we have an open circuit, the meaning of this transduction coefficient is going to be the voltage divided by the velocity. And similarly for the mechanical side. So these are important because we think of these in physical ways, okay? Now, it turns out, yeah.
Can you actually measure these physically?
That's the big point here.
Okay.
Yeah, and you'll go through this again and again in the lab. That's right. These are all they're all measurable, at least in principle. And the big point here, I've already said it once, and let me say it again, is it's much easier to do electrical measurements than mechanical measurements. Okay. So, along that vein, so we're highly prefer to do electrical measurements here. We want to define, there's two more quantities we need to define here that we'll be dealing with that are convenient. And here they are, okay. The first one here, you can see it's an impedance. It's the voltage divided by the current, but not for a blocked transducer, but when there's no force. Again, this is so important, we have a name for that. It's called free. So a free transducer is one where there's no force. An example, take a loudspeaker, put it in a bell jar, and pump it down. A loudspeaker in a vacuum. What's the force? Now this F here is the force due to the fluid. You know, it's the force of the fluid on the radiating surface. There's no fluid, it's a vacuum. So free means no force. And now if you look, this takes a little bit of thought, but you can actually do it in your head. If we look, we want to look at this is the electrical impedance, the voltage divided by the current for no force. So we want to look at V divided by I here, but these are neither of these are in general zero, right? How do we get an expression for that? Well, we zero out the force here, then we can find the ratio of I over U and substitute it. We can put it back into here. So it's a simple. You can almost do this in your head if you think about it. We want to get V over I under conditions of 0F. We need to get that information in there. And when you do that, it's just simple algebra. Here's what you get. Here's what you get. So already this is interesting. So let me explain here. Remember, when we block the transducer, the electrical impedance here is just ZE. That's the meaning of ZE. When we unblock it and in fact go to the limit where there's no force, you can see how the impedance is changing in here. So you feel this, you will feel this, and you know this has to be the case. An external agent electrically driving our transducer, it's going to know whether the thing is blocked or free or somewhere in between. You're going to feel it, you have to. Right? Basically by energy conservation. You know, it's got to be there. So here we see explicitly mathematically how the impedance is changed when we go from blocked to free. You have this additional term here. Now, the same on this symmetric here, we can do the same thing for the mechanical impedance. It's the same idea. And now, remember before, we had no current, right? Open circuit. Now, what's the opposite of that? It's a short. We call it a short. So, analogous to the free case, where there's no mechanical force, is where there's no voltage, which is short circuit. So you can do the same analysis, just flipped, to find an expression for this, and it's given by this. And the same statement I said before applies here. Now, reciprocity is already starting to poke its head up here. Okay, let me explain that. You'll notice that this gives, if one of these, either one is 0, it gives no contribution. Which is maybe is a little bit surprising. You might think here in the electrical case, you might think that it's going to have to be one of them, but it's either one. And this, I think this is reciprocity starting to appear. But we'll go over this in depth. We spent time on it last quarter. We'll spend more time than we did last quarter on it this quarter because it's more important here. And we'll do that on Monday. Okay, so see, I just did this. So, like I said, let me remind you, you entirely expect, if you go in there and monkey with the transducer, you make it, free instead of blocked, you're going to know that. You're going to be able to see that. You're going to feel the external agent that's electrically or mechanically it works the other way too. But if you're electrically driving this thing and you're playing around with the mechanical side, you're going to know it. Because they're coupled. The mechanical electrical sides are coupled here, as long as these aren't, the transduction coefficients aren't 0. And it works mechanically too. Same idea. Now we're going to start to see this bias that people have because it's a lot easier to make electrical measurements and mechanical measurements. This quantity right here, this is how the electrical impedance gets modified due to the motion. Okay, remember when this is not here, we have no motion, it's blocked. Here's the other extreme case where we have 0 force, so there's motion. This tells us how the impedance gets modified due to the motion. This is so important that this quantity right here has a name. It's called the motional impedance, and we'll encounter this again and again in this class, the motional impedance. And you might say, okay, so what do they call this? They don't call it anything, okay? Because usually this is much more important because of our bias. We want to make electrical measurements. They're so much easier than mechanical measurements. So you'll see this again and again, this motional impedance. Right, okay, that's good. Okay, any questions so far? Anybody ever seen anything like this before? I had never seen anything like this. Anybody seen something like, this is, but this is, people will do theories. That's one of the things we do, humans do. We'll do a theory we'll make a theory out of anything, right? So, and the advantage is obvious, right? You don't want to have to look at each transducer by itself. You don't want to have to go in and do some kind of zoology where you're just empirically classifying transducers. You want some kind of general theory because it can save you so much time and trouble trying to make a transducer, for example, to do a certain purpose, if you have some theoretical basis. Or if you have to modify a transducer. That's another thing I don't think I've mentioned here. You know, you can buy transducers and maybe everything will work out and you don't have to worry about them. Just treat them like black boxes, which what a lot of people do, right? You don't care what's in there as long as it works. But sometimes, especially in research, you have to go beyond that. And which means sometimes you have to modify some commercial transducer. So having, you know, basic theoretical knowledge is indispensable here. And sometimes you have to make your own, right? Okay, so the final thing we want to talk about here is, and this is less important than what we just said, but ultimately it's got to be here. We're going to have loads on here. Now this is a little, I got confused by this. This is really a superposition. In practice, let's say you have a loudspeaker. You're going to be driving it here. You're not going to worry about this load of the loudspeaker. You're just going to have, you got a loudspeaker that's going to deliver voltage and you're going to get a current here. You don't really care about this. What you care about though is, you know, it's going to be loaded. You're going to get some radiation, which is going to be represented by this load right here. Okay? And then the other side is, if we have a microphone, okay, we have a sound wave coming in. This is what we care about here, is we're going to have some electrical load. We don't care about this. So, how do we deal with the more general? I guess one way of looking at this, we've done these special cases of where we've had the mechanical load is blocked or free. Okay, blocked is where this is open here. Free is where you just short circuit it. We're electrically biased, aren't we? You know, we view this electric. You'll notice we really think electrically here. It's a natural thing to do. The free case is we imagine a wire here. We're short circuiting it on the mechanical side. But we want to look at the general case now, just briefly. We'll have some kind of load there. So that's what this diagram represents. But it's really two cases. It's, you know, the case going this way and the case going there. They've been superposed here. Now the first thing you need to notice in dealing with this is a little tricky, and I'll point it out to you in the future when we encounter it. But you might say, oh, this impedance is just the voltage divided by the current. Well, it's not quite right. Because you'll notice here, when there's a positive voltage, okay, which way does the current go through the load here? It goes this way. But this is the positive direction for our current. So it's just, this is the way because we're focusing on the transduction here, a little price we have to pay is these loads here. You got to put a minus sign in there. So the load on the electrical side here, the capital L, electrical, it's the voltage divided by the current, but you got to put a minus sign there because it's going the opposite way than how we define it. And similarly for the mechanical. Now, what Brian says is, if we want to see the natural question is, what's the electrical point driving impedance now that we have a load? So neglect the if we want to care about the electrical input here, when we're driving this, again, we don't care about this, but we need to get this into the canonical equations. You can actually put this into the canonical equations and solve for it, but there's a trick. And I'm surprised Brian didn't mention it. Maybe because it takes a little bit of words here. But here's the trick. Let me show you. We know this. Okay? We know the input electrical impedance when we have no force, right? So what does that mean? What does no force mean? Well, it means we short circuit this, right? Well, why don't we just take this, absorb it into here, two impedances in series add, and then we have a short. So all we have to do to find out what the electrical impedance is with a load here, we go back to our what we had before. We go back to here, which we saw before. We go back to here with the shorted, the free, and we replace. What we do is we replace this Zm with Zm plus Zl. You know, we just take this and absorb it here, and then we can interpret. We are free to interpret that way. So that saves a fair amount of algebra there. So here's what you get when you do that. See how this is the Zm here? It's been replaced with Zm plus Zl. So when I was reading this the first time, I looked at that and I got suspicious that there was an easier way of doing this, and then it hit me much easier. So we can just do it, and this is going from the other side, mechanically, the mechanical input impedance. This is the electrical input impedance. You notice the capital N and the lowercase n, okay? Now, again, we now identify here this, remember this is the blocked electrical impedance. We identify this as the motional impedance. So it's called capital, it's got a capital M on it there. This is the motional impedance. Here. This is not, we don't need to worry about this, but it is peculiar. I think I got this from Brian. You'll notice here the impedance is the mechanical impedance. This is an electrical impedance here, capital letter. You'll notice that there's this kind of inverse relationship here. What that means is if one side is resonating, the other side is anti-resonating, if you think about it. I make a little comment on here. And you know, I don't have a physical feel for that, but it does kind of seem reasonable. It seems like both sides resonating was too good to be true. Like it would violate energy conservation or something. I don't think that's the case. But and it's not going to be really important for us, but Brian does point it out here that we have, this is downstairs, which has this it does have this rough consequence here. That resonance on one side roughly tends to be anti-resonance on the other side. Okay, we made it through. So Monday we'll do reciprocity, right? Anybody have any questions? Any general course problems? We're okay? The first lab is next week? Okay, Savas is still not here, right? Wow, there may be complications. I don't know. Anybody know?
I guess.
Yeah, the baby's
like 2 nights ago.
Oh, okay. I didn't know. I don't know. I'm